just wrote this in advance so you can see it, so I don't have to spend time writing it, but I'm going to erase it and start the lecture soon. So it's going to be divided up basically into 3 parts. And the first part, I'm going to start with the very, very basics of supersymmetry. So I was told that the class would be mostly first-year students of PhD. So I'm not assuming you've seen supersymmetry before. I'm really going to start from the beginning. So I will assume that you have seen quantum field theory and sort of the basics of representation theory and the Lorentz group. But I won't assume anything about supersymmetry. So we'll really start at the beginning. We'll work out the standard stuff about representations and supermultiplets and superspace and superfields. Construct the basic SUSY Lagrangians. And then talk about some more advanced topics like R symmetry, non-normalization theorem, and supersymmetric moduli space. So that'll be the basics. That'll be like the Wesson-Bagger type of material. So here are some references, by the way. So Wesson-Bagger is something, of course, which everyone who studies supersymmetry has basically completely memorized. I'm just kidding. So that's Wesson-Bagger. Really just the first 7 or 8 chapters. Then there's the part on supergravity that nobody ever reads. Okay. And then these are 2 sets of lecture notes that can be found online for free. One by Philip Argyris and another by John Turning. John Turning turned these lecture notes into a book called Modern Supersymmetry. But basically, the material is all contained in some Tassi lectures that are online for free. Okay, so that'll be the first part. And then we're going to talk about dynamical SUSY breaking and SUSY breaking more generally. So some of the guidelines for dynamical SUSY breaking and then some classic examples of models which break SUSY spontaneously or dynamically. And so here are some references for that. Also online lecture notes. One set of lecture notes more recently by Trilligator Seiberg, and another older set of lecture notes by Jörg Koppitz and Sandeep Trivedi. Also in this Turning lecture notes, there's a lot of material on that. Okay, and then in the last third of the course, we're going to be talking about SUSY breaking at the TeV scale. So some more phenomenological motivations for SUSY. That would be starting with the MSSM and all the moving pieces in the MSSM, like the soft SUSY breaking Lagrangian, the classic problems of the MSSM involving flavor and CP, and some of the ideas people have for getting around those problems. This is what's known as SUSY breaking, mediation of SUSY breaking. And if there's time, we'll talk about the Higgs in the MSSM. And if there's not time, that's okay. I think Raman Sundram is going to cover some of that in his lectures too. And so here are some good references for that. There's actually a pretty good textbook about the MSSM called Sparticles. And then, of course, Steve Martin has a SUSY primer that has got many, many citations. Everyone, I think this is a very good reference. And Judith and Rakatsi have a very nice review of gauge mediation, which also has some basics of the MSSM as well. Okay, so that's the plan of the lectures, and here are some references. And so I just want to encourage you all to interrupt me with questions as much as you want, as much as you can. And especially if something is not clear, since I don't exactly know the level of the audience. So if anything at all is not clear, please don't be afraid to look dumb or anything. Just ask your question. I'll very much appreciate that if you interrupt me with questions. Okay? All right. Oh, and one last thing is, I don't know about this final exam thing, but yeah, so I'll be probably just mentioning along the way some things that I'm not going to prove that would be good sort of exercises for you to do, and then you can just do those. For those of you who need something like that, you can do those exercises, and I'll grade them or something. Yeah. Okay, so let's get started. Is this the eraser?
Yes.
Okay, so before I really get into it, I did want to start with a little bit of motivation. Okay, And sometimes, so sometimes it's good to keep these motivations in mind during the darkest days when it looks like supersymmetry will never be discovered, and et cetera, et cetera. Sometimes it's good to remind ourselves why we study this. So, just a few words about motivation. So there are many reasons to study supersymmetry. It's sort of woven into our entire field, the subject of supersymmetry, whether you work on string theory or LHC, collider physics, you're expected to know something about, a little bit at least, about supersymmetry. And really, it's never, you can never know too much about supersymmetry. So it's really part of the fabric of our field. And so this is for, I think, a number of reasons, okay? And the fact that it could be discovered at the LHC is only one of those reasons. Okay, so I just want to remind you maybe of a few of the other reasons also. Okay, so the first reason I think it's worthwhile to spend your time studying supersymmetry is what I call the Mount Everest reason, which is when they asked the first European explorers, why did you climb up Mount Everest? Why would you subject yourself to that? I think one of them famously said, because it's there, right? So, because it's there. All right, and so what do I mean by that? Well, supersymmetry has one very nice thing going for it, which is that it has a uniqueness property, right? So Susie is the unique extension of the Poincare algebra. So it's the unique space-time extension of the Poincare algebra. Okay, so I'll be going a little bit more into detail about this in a moment. So here I'm just going to mention this, but this is the this is called the Haag-Lozanski and Sonius theorem. Okay, so it was proved by these people in the 70s. And it's the famous loophole to the Coleman-Manjula theorem, which says that says incorrectly that there are no space-time extensions of the Poincare algebra. Okay, so I'll talk a bit more about that in a moment, but just by way of motivation, okay, so just mathematically, so we know that to at least very, very good accuracy, there's this Poincare symmetry group of nature, okay, and it has just one unique space-time extension, which is supersymmetry. Okay, so in our experience, nature doesn't give us something so beautiful only to not do anything with it. So there is that sort of prejudice, right? And even if it ends up not being directly relevant, say to the LHC, it's still there, and it's still something which is very compelling to study because of its uniqueness. Okay, and okay, so that's one reason. The second reason is, of course, the hierarchy problem, and maybe this is the one the people in the room are more familiar with, right? So there's this famous hierarchy problem with the gauge hierarchy problem, which afflicts the Higgs particle in the standard model, and more generally, it's a problem of all fundamental scalar fields. Okay, so let's recall in the standard model, there's three different parts of the standard model, right? There are the gauge fields, there are the matter fields, the fermions, okay? And then there's this last thing which was just discovered, which is the Higgs, right? And before the Higgs was discovered, of course, it was a possibility that there was no Higgs, and that it was all strong interactions, like Technicolor or something. Okay, but now we seem to have discovered something which really is looking more and more like the Higgs. All right. So the hierarchy problem is a problem for the Higgs particle, and it's useful to keep in mind the story, how it works for the standard model fermions. So why is there no hierarchy problem for the fermions? So let's recall in the standard model, something that you should all know, which is that the fermions have something called chiral symmetry. Okay, which means so the fermions have a handedness. Okay, there are left-handed fermions and there are right-handed fermions. Okay, and the handedness refers to their transformation properties under the Lorentz group. Okay, and so what chiral symmetry is the possibility of rotating the left-handed fermions or the right-handed fermions independently of each other. Okay, so I can rotate, for instance, just the left-handed fermions in the standard model, and this is almost a symmetry of the model, right? So it's the only thing that breaks this symmetry. Does anyone know what breaks this symmetry? Yes, so the mass equivalently with the Higgs, the Yukawa coupling, right? Good. So in the standard model, there is the mass term, okay, which couples together psi left and psi right, and this breaks the chiral symmetry explicitly, right? So the mass terms, as they are, break the chiral symmetry explicitly, and so this breaks chiral symmetry, but it's the only thing that breaks chiral symmetry. All right, so that's good because now when we come to talk about the radiative corrections to the fermion masses, that is, so this being quantum field theory, the parameters are never what you think they are, right? But they get all sorts of corrections when you go to higher order in perturbation theory, right? So the fermion masses like everything else, receive radiative corrections. So, for instance, we could have some fermion coming in, and then gauge loop like that, right at one loop. Psi left, psi. Psi left, psi right. Yeah. Okay. So in the absence of this explicit chiral symmetry breaking by the mass, this loop would not give you a correction to the mass, right? So this is some correction to the mass. All right. So it's a term in the effective action that couples together psi left and psi right. Okay. So in the absence of chiral symmetry breaking, okay, this would be 0. It would be protected by the symmetry. So diagrammatically, you see that because you have to insert at least one power of the chiral symmetry breaking to make this diagram even possible. Okay, and so what this tells us is that the value of this diagram, so it has to vanish when I take n to 0. Okay, so this is proportional to n. All right, and we also know that in quantum field theory that diagrams like this diverge, right? They're not finite, but they're divergent, usually. Okay, so but just by dimensional analysis, we can tell how this thing is supposed to diverge. Because this has dimensions of mass already, right? So the only way it can diverge is like a law. Okay, so this is what chiral symmetry does for you. Chiral symmetry breaking and chiral symmetry does for you. For the fermion masses, it tells you that the divergence is at most a log. Okay, and as long as the mass parameter is small, then the one correction to it is also small. Okay, so the radiative corrections are proportional to the small parameter of chiral symmetry breaking. And they are only log divergent. Okay? And so this is an example of something called technical naturalness. Which means that once you've set the fermion masses to be small, say relative, what does small mean, by the way? Well, small here, it's a dimensionful thing, right? So small means relative to some other thing with the same dimensions, right? So the thing with the same dimensions that we're comparing it to here is this lambda, which in this calculation functions as the role of the cutoff of the theory. Okay, so we do this loop diagram up to some cutoff, lambda, and that cutoff is supposed to be the scale at which new physics enters into the theory. Okay, so that could be the Planck scale. Okay, but so even if it's Planck scale, the log of a Planck scale is a relatively small thing. Okay, and if this n is small compared to the Planck scale, this will continue to be parametrically small compared to the Planck scale. Okay, so that is what goes by the name technical naturalness, and that is a well-known and very nice property of the fermion masses in the standard model. And more generally, any fermions in any QFT. Okay, so now the reason I went through that in some detail is because it's useful now when we come to talk about the Higgs. Okay, so compare with the Higgs in the standard model. So the Higgs does not enjoy any Chiral symmetry like that, right? So the Higgs mass looks like, and there's no way to rotate the Higgs and say not the Higgs star, for instance, to get something like Chiral symmetry. Okay, so this enjoys no analog of Chiral symmetry, right? And so that means that there's nothing protecting the Higgs mass. There's nothing protecting the Higgs mass from these divergences. All right, and so you can see that explicitly. If you haven't tried this at home, you should, which is, just calculate, for instance, this loop diagram, right? Just in the standard model, the Higgs couples to itself, right? The Higgs also couples to, say, what fermion does the Higgs couple to very strongly? The Higgs couples to the top very strongly, right? So this loop here is also a divergent loop, all right? And these are both contributions to the Higgs mass, right? Which by dimensional analysis has to be a mass squared, actually. Right? So scalars have this annoying property that they go like mass squared. They're these diagrams. Okay, so this is a correction to delta m squared. And there's no symmetry in the standard model that would imply that these things are, there's no approximate symmetry in the standard model that would imply that these diagrams are small. Okay, so when you actually come to calculate them with some UV cutoff, you get this disorder lambda squared. Okay? And so this is the hierarchy problem in a nutshell. So if lambda here is the scale of new physics, okay, so if I calculate all these different diagrams, and then they all give me something proportional to this cutoff scale, right? And then I'm supposed to get out what is the value of the Higgs mass. We've gone and measured it in the lab, and it's pretty accurately, it's 125 GeV, right? So all of these different divergent contributions, plus whatever the counter term is, right? They all have to add up and give you 125 GeV squared, right? So if, for instance, so if lambda were the Planck scale, so if we wait until we get to the Planck scale to cut off this loop, well, that looks very funny then, right? Then the one loop correction to the Higgs mass goes like m Planck squared, and all these different corrections plus the counter term, they all have to cancel each other to give us 125 GeV, right? So cancellations to get 125 GeV squared. Well, at what level do things have to cancel, right? If I have some number, what is the Planck scale? It's 10 to the 19 GeV, right? So if I have some numbers which are, I have 19 zeros after them, and I have to cancel to get something, it gets squared, right? So that's 10 to the 38, right? So something with 38 zeros after them, and I have to cancel to give me something with 4 zeros, that's a big cancellation, right? So that's of the order of, say, 10 to the 4 over 10 to the 32, sorry, 10 to the 38, which is 10 to the minus 36. Okay, I guess if I include some loop factors and things that, yeah, if I include some, wait, sorry. The reduced function, well, anyway, it doesn't matter. So you either get 10 to the minus 36 or 10 to the minus 32, depending on how you do the estimate. Either way, that's not the point. The point is this is a ridiculously huge amount of cancellation, right? So this is the level of fine, so 10 to the minus 32, fine-tuning that's required if you cut off the theory at the Planck scale in the standard form. Okay, so so that's the hierarchy problem in a nutshell, and it suggests, well, it suggests a few things. Well, okay, so if you want to, you could say I don't want to even solve the hierarchy problem because why? There's an even bigger hierarchy problem out there now. You know, now that we discovered the cosmological constant, there's an even bigger hierarchy problem out there that we're not even trying to solve here, right? So the standard, the propaganda, anyway, I'm not going to really improve on that, but the propaganda is always that this happens all in field theory. Okay, this happens at any intermediate scale in field theory. Okay, and we have many different ideas to solve, so it's fruitful to think about how to solve this in field theory. And these predictions for the LHC, and some of them may be discovered, right? So it's something to do. For the cosmological constant problem, it happens, you know, at the, really that's something having to do, so you don't see the cosmological constant in field theory. It's something that's intrinsically gravitational, okay? And yeah, so it's something that's intrinsically gravitational, and so we don't really understand the theory of quantum gravity, and who knows, maybe there's some magic that happens at the quantum scale. We can't rule out that possibility. Okay, so the gauge hierarchy problem that we're talking about here is something that's intrinsically a problem of four-dimensional field theory, and it has a field theory, or it has many different field theory solutions. Okay, so, and what is one of those solutions? Well, one of those solutions is, of course, supersymmetry. So this hierarchy problem implies a few things. So first of all, it implies that the new physics, okay, the new physics, what should this cutoff scale be if there's going to be no fine-tuning at all? Well, it should be at the same level of the Higgs mass itself, right? So no fine-tuning at all implies that lambda is of the order of the weak scale of 100 GeV, right? But we haven't discovered anything at 100 GeV other than the stuff we know about, right? So, okay, so that's not completely true because the limits from the LHC and from all previous experiments on many things are still at the only 100 GeV level. That includes anything that's like a scalar version of a lepton. So anything that's not charged under QCD, the limits are actually quite weak for a lot of those things. And of course, it depends on how they decay, et cetera, et cetera. But in supersymmetric models, for instance, it's very common that the limits on leptons and Higgs are at the 100 GeV level still. Okay, so it's not completely true to say we know for sure there's nothing at this 100 GeV scale. The thing we know pretty for sure now is that there are no colored states whose mass is 100 GeV. Okay, the colored states appear from the LHC to be much heavier, at least 500 GeV and probably more like a TeV. Okay, so the fact that there's the direct collider bounds pushing up against this 100 GeV naturalness prejudice, this is what's called, so no new physics so not quite no, but there are some limits on new physics at the 100 GeV scale. This is usually what's called the little hierarchy problem. Okay? So you'll probably be hearing a lot more about the little hierarchy problem from Ron's lectures. And the hierarchy problem. Okay. So that's one thing that these basic considerations suggest, is that there should be new physics at the weak scale. And used to be people would say, oh, there should be new physics at the 100 GeV scale. That's getting harder and harder to imagine. So now we say there should be new physics at the TeV scale. We see this is an intrinsically squishy thing. We don't find new physics at the TeV scale. Maybe your students in like 10 years or 15 years will be saying there has to be new physics at the 10 TeV scale. Who knows? This fine-tuning stuff is just intrinsically not precise, right? It's not a method. You will not be able to disprove. It's not like being pregnant. You can't be just a little bit pregnant. You're either pregnant or you're not. Here, things could just get more and more fine-tuned. Eventually, we'll discover new physics, or not. Okay, so this is really a motivation and not a mathematical theorem. Okay. So the other thing that this implies is that there should be something. So even if there's new physics at the scale of 100 GeV or a TeV, that's not enough, right? That new physics has to then cancel all the divergences above its scale, right? And so how's that going to work? So just sticking in new physics doesn't solve the problem. If anything, that might make the problem worse, right? That new physics has to also explain why these things are canceling above its scale, right? And so the way that works, so supersymmetry is one such idea for how the cancellation works. Okay, so SUSY is one solution to the hierarchy problem. And essentially, what SUSY does is very elegant. It extends the chiral symmetry. Okay, it extends the chiral symmetry of the standard model to the Higgs. So, as we'll see, SUSY relates the properties of bosons and fermions, okay, and it puts them in multiplets. Okay, so so anything that within the limit of exact supersymmetry, any property that a fermion enjoys, other than of course its spin, then the boson will also enjoy that property. Okay, so that's an implication of supersymmetry. And so for the Higgs, there will be in the same supermultiplet, the Higgsino, okay, and this Higgsino being a fermion, a biofermion, will enjoy a chiral symmetry of its own. Okay, so supersymmetry will extend the chiral symmetry of the Higgsino to the Higgs. Okay, so in this diagram, for instance, so when you actually come to calculate the diagrams, what you find is that so for every diagram in the standard model, in the limit of exact supersymmetry, there will be an analogous diagram involving a superpartner running in a loop. Okay, so that superpartner we usually denote with a squiggle. Okay, so the Higgsino, for instance, will run in a loop whenever the Higgs can run in the loop, and the magic of supersymmetry will be that these exactly cancel each other in the limit of exact supersymmetry. Okay, and similarly for the top loop, okay, the tops also. So the tops are fermions, okay, so they live in a multiplet with some scalars, and so those are called the stops, scalar tops, okay? And so this diagram will have, a friend, which cancels it. Where the scalar tops run in the loop. Okay, so the fact that they cancel is a consequence of this chiral symmetry that gets extended from the fermions to the bosons. Okay, so that's what I wanted to say by way of motivation for SUSY. Are there any questions about that? Okay. All right. I probably also should have added that another motivation of SUSY that goes along with the first one, the fact that it's there and that it's unique and mathematically elegant and all that, is that it allows us to study many theories. If you take a theory that you want to study, say QCD, you don't know how to go about it because it's strongly coupled, and then you add supersymmetry to the mix to get basically a toy model of it, a toy version of it, which also has strong dynamics. Then the fact that you added supersymmetry to it can often allow you to say much more about it. Okay, so a theory that has supersymmetry, you can say much more about. Okay, it enjoys many special properties because of that supersymmetry. And so that's a common game that puts food on a lot of people's tables, is to study toy supersymmetric versions of theories you care about, to learn a lot about them, and hopefully at the end, you learn some lessons about the theory that you started with. Okay. All right, so that's probably enough time to spend on motivation. So now I want to get into the real meat of the course, talk about the basics of supersymmetry. All right. So any discussion of SUSY basics usually starts with some mention of a very nice and famous no-go theorem of Ullmann and Mandula. They said that in D greater than 2, QFT with a non-trivial S matrix implies, so if you have a QFT with a non-trivial S matrix, then its symmetry group can be, at most, Poincare times internal symmetries. Okay? So the symmetries of any interacting QFT in greater than 2 dimensions, according to Ullmann and Mandula, can be at most the Poincare group. So what's a Poincare group, by the way? You all know what the Poincare group is?
Lorentz plus translations.
Lorentz plus translations, right? So Lorentz group, which is SO3, 1, plus translations. So that's the symmetry group that we all know about. And then, of course, there can be internal symmetries. For instance, we know there's charge, there's, and I'm not even counting gauge symmetry in this list because that's not a symmetry, more that's a redundancy of description, right? So the actual symmetries of the theory are Poincare times, we can have as many internal symmetries as you want. Okay, so this is the famous no-go theorem of Ullmann and Mandula, and I'm not going to prove it here, but the idea of the proof is that if you try to extend the Poincare group in any way, in any non-trivial way, okay, so if you have any more space-time symmetries, for instance, what would be an example of that? You could have, for instance, a higher spin current, conserved current, right? You could have, for instance, a higher spin symmetry. So that would then lead to, so any non-trivial extension of Poincare. So this would lead to, so basically your S matrix would have to transform under these new symmetries, right? And that would imply, so what they worked out is that would imply so many restrictions on the S matrix. Okay, each such restriction is sort of like a constraint on the S matrix, right? So that would apply so many restrictions on the S matrix that it would become trivial. They proved that the only solution to all these new constraints, the moment we had one more generator, all these constraints are so constraining that new constraints on the S matrix, and then the S matrix must be trivial. Yes.
When you say trivial, you mean the identity or that the angles are discrete?
That's a good question. So I meant trivial as in the identity, but maybe there is the possibility of discrete in their proof. I don't remember now. Yeah, but that maybe they reduced it to that case where like they can only scatter into discrete angles, and then there's no known way that we could get an S matrix that looks like that. I have to go back and look it up. Okay. But what I meant is basically the identity, and the question being raised is maybe it's not quite the identity, but it's some discrete, version of the identity. So we can only scatter into discrete angles. So the identity would be that they just pass right through each other. Right. Okay, so that's something to check. Right. So that's the idea of their proof, and there was nothing wrong with their proof. But there is one famous loophole to their no-go theorem. And in general, that's the value of any no-go theorem is in the loopholes, right? So, and this is the famous loophole that leads to supersymmetry, which is that Coleman and Mandula only consider standard, that is to say, bosonic extensions of Poincare. Okay, so maybe at this point I should actually write down what I mean by the Poincare algebra. So the Poincare algebra has, we always talk about the generators of a symmetry group, right? So the P mu are the momenta, right? And they are also the generators of translations, right? And then the generators of Lorentz group are usually packaged as these anti-symmetric 4x4 matrices, M mu nu. So these are anti-symmetric, and mu and nu run from 0 to 3. Okay, and so these are the generators of Poincare, and Coleman and Mandula, they said, let's try to extend this algebra with other bosonic generators. So like J, mu, nu, rho, for instance, would be one example. Okay, so let's try to extend the Poincare with other bosonic generators. And then they proved what they proved. Okay, so but they left out one interesting and maybe probably at the time completely bizarre case. Bizarre because it has no classical analog, right? So with fermionic generators, the Coleman-Mandula theorem can be debated. Okay, so if, for instance, we consider some new generators which have, half-integer spins, okay, then by spin statistics theorem, they should be fermionic. Okay, then these generators can have a non-trivial algebra with the Poincare group without implying things about the S matrix. Why do they not imply things about the S matrix? Well, the way you get some constraint on the S matrix is you commute these new generators with your S matrix fields. So the S matrix is basically a bunch of correlation functions. Right? You have a bunch of correlation functions, say phi x1, phi x2, right? That's the typical S matrix thing. And using bosonic generators, if I commute them with things in my S matrix to get relations, to get constraints, okay, they will automatically, return the fields that I started with, right? Because everything's bosonic. The difference with these fermionic charges is they won't give me back the same S matrix element. I have to act twice with them in order to get back the same S matrix element. Okay, so that way I don't get a constraint. I get just some relation between two different two different fields in the theory, in the SMUCs. Okay. So that's how, with fermionic generators, the Cohen-Mandela theorem can be evaded, and what Hogg, Lopuzansky, and Sonius showed is that the unique extension of Poincare is the supersymmetry algebra. Okay, so there is a Coleman and Mandela-like theorem when you allow for fermionic generators. Okay, it still tells you there is still some. It's not like once you allow for fermionic generators, you can do whatever you want, right? Because if you have twice the fermionic generators, you can get back to the Bosonic one, right? So there should still be some restriction, but that restriction is of course looser and allows for one thing, which is supersymmetry. Okay, and actually you can get basically the whole supersymmetry algebra, pretty much, once you specify what the generators are. And so essentially, what these people proved is that at most can add the two charges to the theory. So you can add Q alpha, spin 1/2 charge, spin 1/2 generator, and Q tilde alpha. Another spin 1/2 generator. This one's left-handed, this one's right-handed. Okay, that's the essence of what these people proved, is that you can at most enlarge the generators of Poincare algebra to have two more objects. The left-handed supercharge and the right-handed supercharge. Okay. So in other words, they proved that what are we leaving out when we do this? We're leaving out, for instance, spin 3/2 charges. So they show that you can't extend Poincare with any spin 3/2 charges. That would again lead to a trivial escalation, et cetera, et cetera. Okay? All right. So, but that's essentially all they showed, because once you say that this is my algebra, P mu, mu nu, and these things, pretty much the rest of it comes from Lorentz invariance. Okay. So what do I mean by that? Okay. So now I want to work out what the algebra is. Okay, so suppose my cast of characters are these objects. Okay, so I would like to figure out what is the allowed set of commutation relations between these charges, right? So let's start with these ones I don't touch. These are Poincare, right? So what are the Poincare algebra? Well, the P's commute with each other, and then the M's. Right. Okay, so the M's, well, anything all their commutation relations with everything else is just determined by Lorentz symmetry, right? So it's determined by the indices under the Lorentz indices that object carries, right? So for instance, the commutation relation of mu nu with p rho is equal to I eta mu rho p nu minus I mu rho p mu. Okay, so I didn't have to derive this. It's basically given to me by the indices that p carries and the antisymmetry of the generators. Okay, and also there's another one. I'm not going to write that one out. Okay. So now the question is, how what happens when I try to extend it with Q alpha and Q alpha dot? Okay, so there's a number of things we have to worry about, right? So what happens when I try to commute Q alpha with the P mu's? Okay. Well, there's no other charge that could go here, right? Well, other than Q alpha itself. Right? Actually, you can't put a Q alpha there because this thing has spin 3 halves. So this has to be 0. And also, this one has to be 0. Okay. What about this one? Do we know what this is? Or do we have to, is there any choice in the matter? Do we know how Q alpha should, the commutator with the Lorentz generators? I'm not asking if you just know what it is offhand. I'm saying, is this determined already? Or is it something we get to choose? 50-50 chance. What? It's determined, right? Yeah, good. So this is determined, again, by Lorentz symmetry, right? So once I've specified how this thing transforms under Lorentz, everything, this is determined. Okay, so this is equal to, I'm not going to write it out, you can find it in the books. So this is determined by Lorentz. All right, so that just leaves us with one. That leaves us with also this one, of course. Okay, so that leaves us with just a couple more things that we have to worry about. Okay, one of them is Q alpha dot. But here's where something interesting happens, right? These are fermionic. So as we know, it doesn't make sense to make commutation relations for fermions, as we know from, say, quantizing the Dirac field, right? Whenever you have fermionic operators, they should obey anti-commutation relations. Okay, so here we have a slight choice, not a big choice, a very, very mild choice, which is, so what should this be? Okay, so what this should be is, again, so we're only allowed to use these objects here, right? And again, we know that this thing transforms under Lorentz symmetry with one left-handed index and one right-handed index, right? So, is there anything where, does that look familiar to anybody? Something which carries one left-handed index and one right-handed index. Yeah? Oh, a Weil spinner carries just this index. Yeah, and anti-Weil spinner carries just this index. But what happens when you mush together a Weil spinner and anti-Weil spinner? Oh, okay, that is also a correct answer, but that's not what, no, yeah, so that is one way you can mush them together. That's if you add them, like vector sum them, right? What happens if you tensor product them together? Sorry? Well, you do get Ply matrices, yes. But what are those Ply matrices really doing? They're converting some set of indices to some other set of indices, right? Yeah? Vector, good. So when you mush together as a tensor product, this is in the 1/2, 0, and this is in the 0, 1/2. Right? So when I tensor these two together, I get something which is 1/2, 1/2. Which is a vector, and is an irreducible representation of the rings. Okay, so the way technically, so what has the indices of a vector in this list? Obviously P mu, right? And the way technically we transform the P mu index into the alpha alpha dot index is through these Pauli matrices, right? So we put a sigma mu alpha alpha dot P mu on the other side. That's the only thing we can do. Up to an overall normalization, which a lot of blood and tears have been shed, I'm sure, over this normalization, and a standard convention is to put a 2 there. Okay? Obviously, I can change that too if I just change what I call the Q, rescale what I call this 2 leads to a bunch of annoying square roots of 2's elsewhere, but apparently if you don't do the 2, it's even worse. Okay. So, all right. So that's this one is the crux of the SUSY algebra, and I'm almost done with the SUSY algebra. There's one more anti-commutator that I have to talk about. What's that? So I've done almost every single possibility here. There's one that I haven't done yet. Q itself, yes. Thank you. So there's one more, which is the Q alpha, Q beta. Okay, so what does this have to be? Do we have a choice here? So this should carry these indices, whatever's over here, right? And the only thing that carries those indices is epsilon alpha beta times the scalar. Right? So this is secretly familiar to when you do like spin 1/2. So spin 1/2 times spin 1/2 gives you the scalar. Okay, so this is the antisymmetric tensor, right? Which is an invariant tensor. It's the scalar. It's secretly the scalar. Okay, so this, what should Z be? Is Z a choice or is Z fixed by some considerations? So if you think a little bit harder, this one's a bit hard to see, but if you think a little bit harder, Z actually has to be 0. So Z has to be 0, not a choice here. Z has to be 0 because this is antisymmetric under interchange of alpha and beta, but this is symmetric under interchange of alpha and beta. So this is Q alpha Q beta plus Q beta Q alpha. This is symmetric under alpha and beta interchange. But this one is antisymmetric. So that implies Z is 0. Okay? So the only possibility here is 0. And so that is, now I've worked out the entire SUSY algebra, and you see that there was no choice really in the matter. Everything was determined for instance. Okay, so that's what I meant when I said the essence of this theorem that Pockworth has proved is that it is only possible to extend Poincare with these kind of terms. Okay, there's one more possibility that I haven't discussed, which is allowed by this HLS result, which is that you can extend it by more than just one set of supercharges. Okay, so there can be another. So you can have n copies of the same thing, and it will still make sense. Okay, and so this is called extended. So extended SUSY. And what I talked about here is n equals 1 SUSY. N refers to the number of Q's and Q tildes, number of pairs of Q's and Q tildes. Okay, so we talk about n equals 1 here, and it's very much in vogue among more formal investigations to study extended supersymmetry, because the more supersymmetry you have, the simpler the theory becomes. So people talk about n equals 2, and also n equals 4. I won't get into why there's no n equals 3. And if you try to go beyond n equals 4, then it turns out your multiplets become so big that they contain fields with spin higher than 1, and so are no longer normalizable QOTs. Okay, so people, so it's standard to stop at n equals 4, but if you're doing like supergravity, which is already not normalizable, then you can go further, go to n equals 8. Okay, so for example, n equals 2 and n equals 4, and the only thing that changes in this discussion, if you do extended SUSY, all of these things that we discussed before are still true. Here you can diagonalize this part of the algebra without loss of generality. Okay, and then the only thing that changes once you've done this diagonalization, you're done with possible unitary rotations of the charges. And then now something interesting can happen here, which is that instead of just being a number, I can have a matrix Zij that goes here. Okay, And so now this is symmetric under interchange of alpha and beta and I and j simultaneously, not just one at a time, but simultaneously. Okay? And so this thing has to be antisymmetric under simultaneous interchange of these two set of indices, which just means that Zij should also be antisymmetric, but does not imply that it's 0. It just implies that it's antisymmetric. Okay, so in theories of extended supersymmetry, this plays an important role, and this is called the central charge. Plays a very important role in the study of what's called BBS condition, which are objects which are enjoy full supersymmetry. They saturate what's called BBS bound, and the central charge plays an important role in BBS bound. Okay, so I think we start a little late, but I can. This would be a good place to stop. Maybe,
if you want, you can go for a bit.
For a bit.
We have to stop by 11.
Oh, but I was given an hour. Right? I don't want to do. Let me just.
Maybe
Okay,
if
so,
you want to say your notation a bit about fermions, I'm not sure if everybody is familiar.
I was hoping somebody would stop me and ask me about that. So nobody did, so I assume it's completely, you're complete experts on alphas and rus and things.
Everybody's familiar with bias primers? Who's
This
not
is some other
familiar?
heads. I told you, don't be afraid to look stupid. You never learn if you're afraid to look stupid. So I can do a little remedial. Yeah, that's
Maybe
fine.
you can go ahead.
Yeah. I do want to mention one thing, so before I forget, which is that, right, so there's one more thing. So we derived all this from general principles, and as we saw, there was no choice in the matter. Okay? So one useful check, though, useful check of consistency. So, I mean, you don't have to check it anymore because this is received wisdom. Other people have checked it. But imagine you were discovering the SUSY algebra for the first time, and you've gotten it by these general means. You want to make sure you haven't made a mistake in your logic, right? And so one useful consistency check you would do is to check what are called the Jacobi identities. So a useful consistency check are the Jacobi identities. Which are, if you don't know off the top of your head, the Jacobi identities are these, all the algebras, or the superalgebras in this case, have to obey these things called Jacobi identities for consistency, and they're basically three, when you have commutators of commutators, they have to sum to 0, right? It's cyclic. Okay, so this, for those of you who need it, this is a homework exercise. So just check the Jacobi identities for the basic n equals 1 SUSY algebra. Yeah, so most of them are completely trivial. Most of them are 0. And the only non-trivial ones are Jacobi identities called, say, 2n's. Okay. So I could talk for like 10 minutes about alphas and alpha dots. Yes? Yes. Right. So, yes. So the internal symmetry is still what this says. Okay. So remember, Coleman and Medjula said that it can be at most Poincare times internal, and so the times really means that these two don't talk to each other. They have no non-trivial commutators with each other. Okay, and so HLS say that it has to be SUSY times internal. So if my theory has any internal symmetries, they will commute with everything: the P's, the N's, and the Q's. So I get 10 minutes of remedial. Or do people, I think people might need a coffee break.
Okay, then we can do the coffee break. And we reconvene at
For
11:30.
homework's sake. For Tomer's sake, coffee break.
And so now you should